Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So, in this class we are going to talk about magnetic resonance image acquisition hardware and so called pulse sequences, just to give you an understanding of how images are acquired. We will also understand some of the contrast mechanisms better. Okay, so this is the overview of the class. We will look at some of the hardware that goes into MR imaging system. I called it instrumentation, but we will only be looking at it superficially, in a sense, just seeing what the components are. So, we will look at the main component, the magnet, the gradient coils, the radio frequency coils, the electronics it contains. Of course, we will not go deep dive into electronics, but just saying that these are some of the parts of the scanner and the imaging console. Okay. So, for the as far as the magnet is concerned, it is a main component, and this is what is required. It is also the most expensive among the components. So, it is typically a superconducting magnet. It is a cylindrical superconducting magnet. A cross section is shown in this figure, like if you see, it is a cross section of the magnet, and it basically has a superconducting wire, which in this case is niobium titanium wire, immersed in liquid helium, which is held at 4 Kelvin. Okay. But that particular wire is superconducting at 9 Kelvin. The helium itself is inside a cryostat, it is encompassed by a vacuum and liquid nitrogen. Okay. So, these magnets require, you do not have to keep filling liquid helium often, but liquid nitrogen refilling is required. The field strengths vary from about 0.5 Tesla to 3 Tesla. There are of course 9 Tesla magnets also available. Some of the higher field magnets are used in small animal imaging, for instance biomedical imaging, and also as research magnets. Okay. So, the interesting part here is that once it is basically the wire is wound around a cylindrical core. It is just energized once, right. So, as soon as the critical temperature is reached, you energize it once, which means that you inject current into it and the current keeps on going, because it is superconducting, there is not much loss due to resistance. Of course, over time all of it will will dissipate. Okay. So, this leads to the magnetic field being set, a static magnetic field being set up. So, static magnetic field will point along the axis of the core of the magnet, right, and it is typically, like I said, between 0.5 to 3 Tesla. Modern clinical magnets are either 1.5 Tesla or 3 Tesla. So, I am not sure where these numbers come from, but I guess these are what are possible given the constraints of size, etc. So, like I said, but since 9 Tesla magnets also exist. So, one problem that you will also run study about is, if you get into MRI, is that maintaining the uniformity of the field is a challenge, which means that across the cross section, right, at every point we have to make sure that it is 3 Tesla and so on and so on, and that is hard to do. So, there are some constraints like that. So, it is basically a superconducting wire wound around a cylindrical core, and once the critical temperature is reached, using liquid helium, you inject it with the current, and that current keeps going, giving rise to a magnetic field. That is the static magnetic field that you use for imaging. Okay. There are now systems, economical systems, where people are trying to use permanent magnets, and there are the portable systems, etc., where they are trying to use permanent magnets, or maybe you do not need such large magnets, because if you are just imaging peripheral organs, right, you do not need such large magnets. So, which brings down the cost of the system. So, a lot of research going on in that area. So, the gradient coils, now we will see a little bit more about this later on. So, these gradient coils are also they basically current carrying wires, right. These wires give rise, these current carrying wires give rise to magnetic fields. They are fit inside the bore of the magnet. So, there are 3 coils, each one of them orthogonal, producing magnetic field gradients orthogonal to each other, right. The gradient coils do not change the direction of the magnetic field, right. They just add an x and y and z dependency on the magnetic field strength. And the magnetic field which I am talking about here, the static magnetic field, and it still points along the z axis. And the x and y dependencies are produced by saddle coils, and z gradient is done using 2 opposing coils wound around the circumference. I have some pictures, I think I will show you. So, what do you mean by it does not change the direction of the magnetic field? So, we saw the let me see if I can draw some here very small. Okay. So, here this is our cross section of the core. So, the direction of the magnetic field is here, right. So, now we want, like, let us say it is a 3 Tesla magnet. So, it will be, we would expect that, let us take these random points here, we would expect the magnetic field to be 3 Tesla everywhere. Okay. So, typically that is true, as long as if you are talking about a nominal field of view. However, no, when I say gradient coils, what it does is the direction of the magnetic field is still the same, it is along the axis, z axis, but the value here will be different. The value, which means the magnitude of the magnetic field, if you can call it that, right. It just creates gradients in this. Okay. If this is the value of the B field everywhere, it just creates a gradient along each of these directions, right. For instance, in this case it is along x, which I have drawn here. So, the gradient just changes the value, but not the direction of the field. The field is still along z, along the static magnetic field still points along the z axis, right. So, and in order to produce these gradients, you need current carrying coils of different shapes, configuration in order to produce these gradients. So, that is what I said earlier, that there for instance x and y dependencies are produced by saddle coils, z is done using 2 opposing coils wound around the circumference of the cylindrical core. Okay. So, here are some examples, right, of the gradient coils. So, for instance, this is the gradient coil we talked about, right, this says 2 sets of wires wound in opposite directions. These are the saddle coils we talked about, kind of, right, x and y gradients. So, depending on the how we make these coils, the gradient is produced along each of those directions. Okay. The gradient amplitude again is limited by the current in the coil. It is very high currents, right, it is very high, 100 to 200 amperes, right. And just to give you an idea of the order of magnitudes, the maximum gradient amplitude is 1 to 6 Gauss per centimeter, or in this case 10 to 60 millitesla per meter, right. So, but the strength of our magnetic field, the static magnetic field is about 3 Tesla, right, 1 to 3 Tesla is what we talked about, and this is the gradient amplitude. The switching times, this is important because when we look at pulse sequences later on, we will assume that these are instantaneous, which is not true. There is something called a slew rate. So, it kind of takes time for the gradient to turn on, right, or to reach its maximum value. And because of this constant switching of currents, turning on and off of currents, there are again eddy currents are induced in the metallic components of the magnet housing, right, and distorting the gradient field. So, there are again shielding for this, etc. Okay. So, once again here we go deeply into hardware. So, these are the hardware challenges in designing a magnet for a system for imaging, right. So, you can imagine, so we have the cylindrical core, you already have a a superconducting wire, which is of course inside a vacuum, on both sides there is a vacuum, so it does not touch anything. But still introducing these current carrying wires will lead to some distortion in the magnetic field, and these current carrying coils are wound around in specific shapes. Once we saw saddle coils, and these are circular coils, etc., and they will also produce some distorting field. How do you handle all that? That is a challenge in some of the hardware design for MRI, right. So, there are some limitations for due to the gradient coil. The self inductance of the coil, again that is what prevents rapid switching off, the gradients, and coils can be made smaller, but if we make the coil smaller, then the field of view is reduced, right. So, there is another actual hazard in this case to the patient, because this rapid switching, the presence of currents, etc., can lead to eddy currents in the patient, right. And so there is some limit beyond which switching speed, beyond which there is some nerve damage, and so that is the limitation that you also have hardware limitation, or in this case biological limitation on the hardware, right. So, once again these are other sets of challenges that go with designing MR hardware. The radio frequency coils, as we have seen, is basically these coils is what it produces that B1 field, right, as we call it the B1 field. They produce the B1 field, and this coil induces the spin precession, and these coils actually also measure the current induced by the spins, right. So, we want to measure the echoes, spin echoes, which we see later. These are also done. So, these RF coils do both the excitation of the spins as well as the measurement, though basically it acts as both a transmit as well as a receive coil. There are all kinds of coils, volume coils which surround the patient, surface coil you just put on top of the patient, they are basically in close proximity to the patient, okay. And again designing these coils, how to get the correct RF field, RF out and shape, the B field, magnetic, etc. This is again a field of study, research in itself, lot of groups, people working on this, right. Once again this is one of the hardware challenges in designing an MR scanner, right. So, the radio frequency coils again comes with different configurations. I have listed some of them here. So, if you are into RF transmission, etc., you should read up more about this and how to design these coils, what each one of them produce, how the acquisition electronics for these things, right. So, but just to understand, for understanding this frequency, these RF coils once again can surround the patient or can be just in close proximity to the patient, and they can be used for both transmitting and receiving RF. The transmitted RF is what causes the spin precession, and the induced currents are measured by the receive coils, right. So, again there are surface and volume coils like I said earlier, right. And the other thing to also keep in mind is that the transmission and reception require very different current amplitudes in the coil, okay, because the emitted current is kind of very small, right. You are talking about the spins in our body causing a current, and those currents are typically much smaller than the B1 field related currents, right. So, you have to worry about that also, okay. So, there is typically a scanning console like all other diagnostic devices. So, like for instance CT also has one. So, the console helps you interface with the MR hardware, it helps to select the imaging planes, set ECG gating, respiratory gating, etc. Okay. It is also connected to the reconstruction engine, so that the acquired data is then used by the reconstruction engine, just maybe it is a processor, embedded system, or maybe just another workstation which can reconstruct maybe 10 to 50 images per second. So, MR is real time imaging system, it just it can be an real time imaging system. It does take some time to set up, but you can do very fast frames. For instance, one application of MR imaging is cardiac cine MRI, as they call it. It is a specialized hardware for it. You can actually image the entire volumes of the heart in one cardiac cycle, right. So, several volumes can be acquired in one cardiac cycle. So, that kind of speed is available. Of course, it comes with this is a separate protocol that has to be installed in your scanner. But again, once again, this is the reconstruction is real time, can do 10 to 50 images or maybe more these days, okay. So, let us go back to how we actually acquire data, right. So, we saw the principles of MR signals, how they are produced, right. Magnetic resonance, what does it mean, or nuclear magnetic resonance in this case, what we how do we understand it, how do we model it, etc., right. But then we are now going to look at in the context of imaging, how are images acquired using magnetic resonance, nuclear magnetic resonance phenomena, and that has to that leads to something called pulse sequences. So, in this next maybe half hour, a few hours or so, I do not know, even less, we will try to understand how this is implemented in an MR scanner, right. So, how do we image planes, how are we imaging 3D volumes of the patient, etc. Okay. So, what the fundamental steps are the following. We have what is called a slice selection gradient, there is a frequency encoding gradient, I think this is also readout gradient. I think this again one more terminology. Once again, if you are not familiar with the terminology, it is fine. If you want to ever get into this research, you should know, but otherwise it is just follow along. There is a phase encoding gradient and followed by image reconstruction, right. This is the 4 steps. So, what do each of these do and how are they used, that is what we are going to see. I will also present some so called pulse sequence diagrams to understand the image acquisition process. Okay. Okay. So, why do we need the size selection gradient, what is it used for? So, now we know that for the as far as the MR system is concerned, we have a fixed B0 field, right. Okay. So, the Larmor pressure frequency is proportional to B0. So, it is the same throughout the sample. Okay. So, when we apply the RF pulse, it tilts, we know that it kind of tilts the static magnetization into the plane, and the precessing spins in the plane induces an EMF, but all of them are the pressure frequencies for all of them is proportional to B0, right. And it does not really help because we will just get one FID, we saw that too, we will get one FID if you can measure that, but that does not tell you where the signal is coming from, what is the spin density for instance in a particular XYZ location. Okay. So, how do we go about doing this? So, the first step is to isolate the cross section by applying gradient fields. This is what we want to do. Okay. This is where the gradient coils come in, right. So, we know what the RF coil does, this is where the gradient coils help to localize X, Y and Z positions, we will see how it is done. Okay. So, if we apply the so called slice selection gradient, right, which is basically the gradient along the Z axis. So, once again remember the direction of the magnetic field is still along Z, okay, just that its magnitude is varied by the slice selection gradient. So, what happens is once you apply a gradient at this rate, right, so many Tesla per meter or milli Tesla per meter times Z, the precession frequency, this is the precession frequency, becomes a function of Z, you can see that here, right. So, by applying a slice selection gradient, in this case that is why it is 0 0 GC, right, the X and Y gradients are off, first we apply the Z gradient. So, it makes the Larmor pressure frequency in the volume a function of Z, right. When I say function of Z here, this is exactly that function, right. So, in this case you can see we have encoded the frequency as a function of position, right. So, now once we have this, at the same time we apply the RF excitation pulse. Now, since the RF excitation is at a specific frequency, there is a bandwidth, we will see that in the next slide, there is a bandwidth associated with the RF pulse. So, it will only excite tissue in a thin section, it will only excite tissue in a thin section, right. And what is that thin section? That thin section would correspond to all the points whose Z position has the specific field dependent Larmor frequency, right. So, in this case your RF pulse has a certain center frequency and a bandwidth, and whichever Z position corresponds to that center frequency and bandwidth, because now we know mu is a function of Z, only those spins will be flipped into the plane, okay, right. So, that is the idea behind introducing. So, this means that we are now only looking at a certain cross section of tissue, okay. So, we look at it better. So, if we look at this a mock up of the patient lying on bed. So, this red line, so this is the Z axis. So, if you look at this mock up illustration, the x axis just indicates the direction Z along the length of the patient, right. Now, you are looking along, so this is just a side view, think of it like the side view, and this is the precession frequency, right. Now, this is actually a function of Z, that is what this implies, right. The red line that you see there, that shows the strength of the gradient, which means that as I move along Z on either side, my precession frequency is slightly changed because of the presence of the gradient, right. If you go back and look at this expression, it is gamma B0 plus GZ into Z, right. So, remember this expression, this gamma. So, at this point the gradient is 0, let us say, right, and as we move to the right and to the left, see the precession the frequency keeps increasing, right. So, which is what is shown in this picture. So, the red line just indicates the strength of the gradient, right. If it is a shallow slope, it is a very weak gradient. If it is a sharp slope, it is a strong gradient. So, which is what is shown here. Now, what does it do? Because it is shallow, going a small delta, right. This is the delta precession frequency, right, and that leads to a very wide slice, correct, right, because the gradient's amplitude is small. A very thick slice of tissue will have spins with pretty much the same precession frequency. So, that is what that formula also tells you. Okay. So, my nu and gammas look the same, sorry about that, but you have to just understand that part. Okay. So, but if you make a very strong gradient, which is what is shown here, then if you go from if a small, this is the bandwidth, if you can call it, in your RF pulse, that leads to a very much thinner slice. For the same bandwidth delta nu, we get a thinner slice, because the gradient is much sharper, which means that if you go a very small delta z, there is a big change in the precession frequency, right, but that is what the gradient does, right, because when you go if Gz is very large, if Gz is very large, let us say, right, it is a very large number, then if you move a very small distance along z, then your precession frequency becomes changes very fast, right, that is what that gradient does. So, which means that if you have a very small bandwidth in your radio frequency signal, that will select only a very small or thin slice of tissue. On the other hand, if your gradient is very small, even if you go for your precession frequency to change considerably, you have to go a very longer distance, which means a thicker slice of tissue. So, for the same bandwidth in your RF signal, you will get a thicker slice or a thinner slice depending on the strength of your gradient, right. So, that is what is shown by this illustration. Okay. So, so that is this way. There are two things you can do. You can select your slice thickness. So, you localize your spins, and you also help select your slice thickness, right. So, this is the idea behind the slice selection gradient. So, slice selection gradient and the RF pulse are kind of turned on simultaneously, which we will see that in the diagram. So, this is a typical diagram that you will see in a lot of textbooks as well as papers, etc. Okay. So, a constant z gradient is applied. So, that is what this is. This is the time axis, the blue lines of the time axis. Okay. So, a constant z gradient is applied, okay, and there is this do not worry about this right now, we will talk about it later when you get the chance at little more detail. This is called the refocusing gradient. So, I will just maybe I will tell you right now. So, the idea is, so once you apply Gz for a specific period of time, right, because the slice thickness is finite, right, we have a finite slice thickness, there is there is a difference in the precession frequencies, because they are between the edges of the slice, right. As you go from one end of the slice to the other, there is a difference in the gradient because of the gradient, and so consequently there is a difference in the precession frequency. So, at the end of application of this gradient, there will be a defocusing of the or dephasing of these spins. Okay. So, that is because of the difference in the magnetization or the magnetic field felt by the spins in the left side and the right side of the going from the left side of the slice to the right side of the slice. There is a gradient, z gradient, which means that they will have slightly different frequencies, which leads to dephasing. So, to rephase them, we just have to apply another negative gradient, same amplitude, but for half the time. Okay, they bring that back into phase. Okay. So, that is what this is for, this indicates. So, this just to explain the diagram in slightly better detail. So, this is when you turn on the z gradient. Once again, this is slightly idealistic, because the z gradient cannot come on instantaneously, that is a certain time before it sets, and it comes on, and this is the time period to which it is actually kept on. Okay. And the time t equal to 0 actually starts here, which coincides with the peak of your RF pulse, and then of course you have the this negative gradient for refocusing gradient, refacing gradient, and followed by which there is the FID. Okay, that is when you turn on the ADC. Okay, but of course FID is actually very difficult to measure. You typically measure something called the echo. Okay, we will talk about that later, but this is the slice selection process. The way you select the slice, do a slice selection is along with the RF pulse, you turn on the Z gradient. Now again the Z gradient is determined by how thick, where which position and how you want image and how thick a slice you want image, right. So, the FID signal that you obtain now after the refocusing or I call it refacing, but it is a refocusing gradient, will correspond to the summation or integration of the signals from all the spins in the slab of tissue, right. So, if you go back, so whatever signal you are getting will be from here again or from here depending on your gradient strength, because only those will correspond to the Larmor precision frequency which the RF pulse will flip into the plane. Okay. So, this is the slice selection gradient. So, but even now only this is just one slice, right, we just do not know, we still cannot figure out x y yet. We have just localized the signal to a particular z location or a range of z location. This because that is why you always talk about slice width in medical imaging, even in the context of CT as well as MRI, because the tissue, the image you are looking at, even though it is flat, it comes from actually a slab of tissue, not just a infinitely thin plane. That is a bad approximation, right. So, the slab of tissue is what we have localized, we still have to do x and y localization. Okay, so we will look at a couple of derivations just to understand what is going on. So, we saw that the precession frequency is a function of your B naught as usual plus your gradient. Okay. That is so your precession frequency is now encoded by your z position at this point. Okay. So, now if you consider two positions z1 and z2 like we saw in that picture, let me go back up and just show you what z1 and z2 are. So, you can say, let us say we can call this z1, this point corresponding to, why do I call this z1 and z2, because they actually correspond to here, right. So, this we call this z1 and z2, right. So, these are again similarly here you can call this z1 and z2, right. So, this will be some delta z, this is your slice thickness, this is slice thickness, right. So, now we can actually show, so for instance for z1 we can write due to, this is a simple manipulation. So, I will not go through it in great detail, right. Similarly, for z2 we can write and we can then figure out after some algebra we can just write your slice thickness as a function of this delta nu divided by your gradient amplitude. Okay. Okay. So, this is the expression that the slice thickness tells you how we can determine slice thickness by figuring out this delta mu as well as by figuring out your Gz, you can set the slice thickness. Okay. The slice position, which is basically the average, can also be written in this form, which is given by this this is gamma bar minus gamma 0, sorry mu bar minus mu 0 divided by gamma Gz. Okay. So, this is again the slice position, right. So, all of these two are the important expressions, right. So, that is one set of equations, right. So, another aspect is basically the RF waveform, right. So, what kind of RF waveform do you want? So, based on this derivation we can say we desire a frequency signal, right, whose frequency content is given by some amplitude, it is a rect function, right, times a rect function of mu minus nu bar by delta nu. Okay. So, which means that the signal, so what do we want, because we just need a a rectangular pulse along the frequency axis, right, corresponding to that particular frequency mu bar of a certain width delta mu. Okay. So, that, and the signal itself, you do the Fourier transform, we can do that signal can be defined to be a delta nu, it is a sinc function of delta nu t is to j nu bar t. Okay. All right. So, this is basically what we are looking at, and in this case this is a sinc function. So, we can plot it, and this what we get is, if you look at it, the envelope of this sinc function is what I will plot, right. So, which is something, this is along time axis, right, yeah, something like this, right. It is a sinc function, and of course, if you want the appropriate localization along the frequency axis, you will have something, the ideal thing to that, right. Right. So, this is along the frequency axis, right, this is along the time axis. So, so these are the expressions which help you determine how, what should your RF pulse look like ideally, and based on that what is your Z position as well as your slice thickness. Okay. So, this is the overall model behind the slice selection gradient. Okay. So, now we can move on, and we can talk about how do we localize along the x and y direction, or basically how do you do in plane localization, right. So, this is called frequency encoding, or I think sometimes it is also readout, frequency encoding direction is also sometimes known as the readout direction. Okay. So, as we saw, the signal received is basically the integration or summation of signals from the excited slide. Okay. So, as we saw that the signal received is now restricted, that is basically the spins that are flipped into the plane by the particular angle depending on how long you have the RF pulse on, is only from a certain slab of tissue, right. However, we do not still have localization, basically no x comma y information or in plane localization is present. Okay. So, how do we spatially encode MR signals? Okay. And the way to spatially encode, the one process is referred to as the frequency encoding. In this case, there is a gradient, additional gradient which is turned on during the FID. Okay. And the direction in which that gradient is turned on is referred to as the readout direction, and it is typically orthogonal to the slice selection gradient. Okay. And we would typically, the readout direction is the x axis, the z axis being the along the length of the patient, and that is the axis along which we apply the slice selection gradient. Okay. So, what is the signal model for this? We will just do that quickly before we go any further. So, the signal in the plane, right, the transverse magnetization after an alpha excitation, that is after the spins have been flipped by angle alpha. So, the mxy of t is given by 0 plus, as we call it, e raised to minus j 2 pi where the symbols have their usual meaning. 1 second. Okay. and this is mxy, and this other term just after is basically just before you flip times sin alpha. Okay, that is the what we have. Okay. So, we have this spins in the excited slice, and we want to model the spatial distribution of the proton density T1 and T2, and we assume that the slice is fairly thin, so that there is no variation. Of course, it is not entirely true, there is that variation, but we assume that it is fairly thin. Okay. But there will be some spatial variation of the transverse magnetization immediately after the excitation, right. And the received signal then we can model as the signal that we get due to that mxy. Okay. And that relationship is typically written in this form. So, I will not go through every inch of this derivation, but just to understand the origin of the signal that we are all working with. So, the signal that is acquired, that is received by the coils is actually the function of the magnetization that has been flipped into the plane, but since there is a variation, right, because of the variable, there is some variability in the magnetic field, etc., there is a variation in mxy, right. So, that is why we have to integrate mxy, and that A is some amplitude, it all the other constants have been absorbed in A. Okay. Now, this is the general signal model that we will be working with, right. Now, we can once again we can make it further simplified by using this expression f of x y is the same as A of m x y. I am excluding that 0 times 0 plus, actually maybe I should not. So, then your signal becomes this integral Okay. So, basically the received signal, if you demodulate it, because that e raised to minus j 2 pi nu 0 t is a very highly oscillatory, right, nu 0 is a very high frequency oscillation, you have to demodulate it. So, if you demodulate the signal, it is basically just this integral, right, which is the integral over the spin density T2 relaxation times, etc., in that particular slice, right. So, then we still need something to make sure that we can localize x and y. Okay. So, the way to do that, way to do that would be to apply a gradient along the x axis. So, what happens if you apply gradient along the x axis? So, the gradient along the x axis would correspond to your frequency, your Larmor precision being changed the following way. Okay, sorry, I have used plus, okay, Gx is the strength of the gradient along x. Okay, so, this is how mu x changes, right. So, of course, you can always compare it with, if when we did the slice selection gradient, we apply another gradient, we applied Gz, changing it appropriately. Now, we have, once we remove that Gz, right, so everything reverts back to B0, gamma B0, right, gamma B0. So, then now if you apply the x gradient again, it is gamma B0 plus Gx into x, right. Now, once we have this, then we have to modify the expression we had written right here appropriately, right, because it is no longer gamma mu 0 nu 0 t, right, nu 0 has been modified because of the presence of the x gradient. Now, when we do that, then we can, all you have to do is, let me just write this one expression, so that we understand where we are going from. So, the signal we are talking about then becomes A, right, there is e raised to minus j 2 pi nu, see instead of nu 0 you have nu 0 plus let me nu 0 plus your gamma g x x into t, right, and then every I have the exponential minus t bar t 2 dx dy. Okay. So, the part that is changed is, and then you can still take out d raised to minus j 2 pi nu 0 into t. So, then what you will get is that signal that you are measuring, right, is basically this, right. So, this is the important concept in MR imaging, right, this particular equation. So, you can now identify. So, we have what we have done is now identify the position with the frequency, right. So, we can interpret this expression as a Fourier transform with one of the frequencies, in the case frequency corresponding to y direction being set to 0, right. So, how do you do that? So, you can set v equal to 0, and we can also set u to be equal to this expression. So, then if you can plug it back in there, and you can see that this is the expression we have is the form of a Fourier transform, right. So, instead of gamma g x t you just put u and v you set to 0, right. So, ux plus v y, right. So, if you just want to write this, if you write this as some function f to infinity f of x comma y e raised to minus j 2 pi u x plus v y dx dy, right. So, if you set v equal to 0, that is the expression we have there, right, set v equal to 0. So, this is basically in the form of a Fourier transform, right, or in this case it is a the Fourier transform where we are trying to integrate over the spatial variables, right. So, we have the spatial frequency corresponding to u and v being defined by here. Yeah. So, this is the way we encode positions using the gradients, right. So, this is one of the fundamental equations for, or this is the fundamental equation for understanding MRI, where we interpret the signal as the Fourier or the Fourier transform of the quantity you are trying to measure. So, this f of x y encompasses everything, right. It tells you about the magnetization as a function of x comma y. It also tells you about the relaxation, the spin properties T 1 and T 2 times. So, in this case T 2 as a function of x and y, this is already encapsulated in f of x comma y, okay. And the application of the gradient along x captures again makes it into the form of a Fourier transform. And one of the terminology that in MRI is that it is called K space, right. So, you will call u would be kx and v would be ky, okay. All right. So, this is referred to as K space, right. So, you would have to measure all of K space, right. So, in order to figure out the Fourier transform, and then you do the invert it, right. So, that is the acquisition strategy in MRI, right. So, this is the first step towards casting it in the form of a Fourier transform, okay. And the way to actually measure would be to scan the so called K space, right, by taking on a range of frequencies. And how do you adjust that? By changing your gradient, correct. That is one way of doing it, is to change the gradient, or the most effective of doing it is changing the gradient. By changing the gradient, you will capture a variety of kx and ky, and therefore, that will give rise to your Fourier transform, that is a k space acquisition, and using that you can reconstruct your image. Okay. That is the interpretation of image acquisition in an NMR signal, in an MR system. Okay. So, how does it work in the for frequency encoding? So, as you saw, the FID is still the integral of all the spins within the slice. Okay. But the Larmor frequency is what we try to do is to modify it according to position within the slice, namely along x. So, because we apply the gradient along x. Okay. Now, this leads to a FID signal that has position encoding, right. Once and we saw that then this signal can be interpreted as the Fourier transform of this spin density, in this case which is m, and of course, it also is a function of T2, right. The frequency variable we identified as gamma gxt. However, in this particular acquisition mode with one gradient, it corresponds to V equal to 0, right. So, this is the pulse sequence diagram, RF turned on, the gradient along Z also turned on for slice selection, the refocusing gradient followed by the application of Gx, it is turned on, again this along the time axis, it is always on, and during which we actually do the ADC, right. This leads to our image being which is like scanning k space, but you see that this here only corresponds to a certain V equal to 0. So, we are stepping along u, but V is still 0, right. So, ADC of course samples these signals in time, u is given by gamma Gx into t. So, that tells you, it gives you the whole range of views, of course, and of course, we have to change V in order for us to sample the entire k space. So, how do we change V, that is another question, we will answer that in the next slide. Okay. So, the MR signal model we have already seen, just to recap, I will write this down as we saw the application of the gradient leads to the following signal, right, SOT right. Then you made the identification that u is this expression, in this case V is 0. Okay. Now, how do we do this scanning, right? Now we saw V equal to 0, then how do we change this, right? So, the way to do that is also to apply another gradient along x, right. So, if you apply another gradient along x, along y, so then your signal model would be this would be your signal model, right. And so, from here we identify the Fourier domain frequencies as xt and V as, right. And so, what is the Fourier trajectory that we are sampling here? The trajectory we are sampling here is obviously we are going in this direction, theta as tan as arc tan Gy by Gx, right, or if you want to plot it. So, if you are looking at the k space diagram, so to speak, so u v by changing Gx and Gy in appropriate steps, you are basically sampling along a certain direction like this, that is theta. So, it will be sampling kind of radially by changing the strength of Gx and Gy, you will end up scanning along arbitrary directions, and then once you have scanned the entire UV, this is called polar scanning. So, once you have scanned the entire UV space, of course, you can do interpolation onto a Cartesian grid and do the reconstruction. Okay. This is the polar scanning protocol. Okay. So, here just to summarize again, the scanning the Fourier space requires the repetition of pulse sequences to, like we saw, because we only have v equal to 0. So, we have to scan for different values of u v in order for us to get to the appropriate positions in K space. Okay. So, this is accomplished by an additional gradient along y direction, it is called a gy gradient. And the application of gradient along x direction with 0 gradient along y made the readout direction x, and of course, the directions can be changed. In this case, we apply both the x and y gradients simultaneously, right, and the pulse sequence has to be repeated with different gradient strengths to cover the different K space trajectories. Okay. So, if you want different angles, then you change the strength of the gradient, you get a different angle, and then you sample along that direction. So, that is the idea behind the polar scan kind of pulse sequence. This is what is shown here, everything else remaining the same, x and y gradients are turned on simultaneously, and of course, you do the ADC acquisition as function of time. Okay. So, this once again, and of course, we keep changing the strength of Gx and Gy to get different angles, right. So, that is what we saw. So, the theta, the angle at which you scan, is given by the strength of Gx and Gy. So, by changing Gx and Gy, so this, I think this is not very clear. Yeah, Gx, right. So, by changing Gy and Gx, you can get different angles, and then of course, you sample along that direction. So, that gives you the K space trajectory. Okay. So, this is for a polar scan, again once again this is probably not, this is just for the concept, right. There are different ways of traversing it, traversing K space. The other way is the phase encoding, right. So, here once we saw polar scan is one technique to traverse K space in 2D. I do not think that is a very common thing to do, but that is I think one of the earliest things that was done. Okay. But phase encoding is what is done more commonly. Okay. So, the frequency encoding is used for readout along u, the u direction in the K space, and the phase encoding is for readout along the v direction. Okay. So, the way it works is we do a slice selective RF pulse followed by a refocusing gradient. We saw that the usual, and this is the one we are talking about, right. This is the RF pulse slice selection gradient. This is usually standard, you will see this everywhere. Okay. And then you apply the y gradient with strength Gy for a certain duration, okay, achieving phase encoding, right. Readout direction is then applied while acquiring data. Okay. Then the pulse sequence is again repeated with different strengths to cover the entire K space trajectory. Now, we might wonder, okay, so first we will look at this diagram first, right. So, what we do is we have the usual RF pulse applied along with the slice selection gradient, refocusing pulse FID, and for usually in the diagrams this comes after. Okay, I have just put it so that in time it looks great, nice. Okay. So, you apply the phase encoding gradient for a specific period of time, right, and then you switch it off, and then you apply the readout gradient right now, and you acquire the signal at the same time. So, what does this accomplish? So, typically what happens is like, so when you have the RF selection slice selection gradient on, then all the spins in that particular slice have been tipped into the field of into the plane and into the xy plane, and they are all processing with the same frequency, okay, which is basically corresponding to whatever gradient plus the B0 field is. See, applying the phase encoding gradient and switching it off, see once you switch it off they all go back to the previous B0, right. So, what does applying the phase encoding gradient accomplish? The phase encoding gradient imparts a phase change. So, they all might be rotating in the same frequency, but they will be off by a phase, right. So, the phase it gives you a position dependent phase, okay, to the rotation if precession to the precession, and that is preserved even after the removal of the gradient Gy. So, the phase encoding gradient only does that, it gives you a position dependent phase value, and then when you do the readout gradient, when you have your gradient on as you are acquiring the data, then there is a position dependent frequency also added into the mix. Okay. So, the way that model works, let us just, so there are some we will look at the model first, but before we go any further, I have been kind of very superficial about this time axis here, right. I am just indicating some arbitrary times. I have not indicated what these times are. These times are actually specific times, right. There is something called time to echo, that is when you measure. There is a time to repetition, because all of these have to be repeated for different values of gx and gy, right. So, when we do that, you can't do it right away. So, there is a time gap between these repetition, that is called time to repetition time or time to repetition, TR and TE times. Okay. Time to echo is when you, it is the middle of your measurement time window. Okay. So, this TE. So, all these are actually very crucial, these timings are crucial, and I have not actually mentioned them. I am just giving you a overall idea of how these measurements are done. So, you understand how it is done, right. So, let us just go back to the signal model if you have the phase encoding gradient, right. So, the phase encoding gradient, what does it do? It's not too different, because now the one thing you have to remember is that we are applying the phase encoding gradient for a fixed amount of time, okay, applied for a Tp, right. And so, the signal model, so we will write down the signal model, but before that we have to see what is the phase accumulated due to this, right. The phase accumulation, like I mentioned before, is a function of position, which is this is a value, this is a phase accumulated. So, your signal model then becomes okay. So, now your u is basically this value as usual, and v is, so this Tp is fixed, kind of figure this out what it should be. So, this is your baseband, so called baseband signal, right. Of course, it is modulated by that exponential e raised to minus j 2 pi nu 0 t, which I have not indicated here. This is the demodulated, this is 0 is the demodulated signal, and this is how you scan the k space, right. So, but by you change u by changing the gradient, you change v by changing the gradient, so on and so forth, right. So, that is how you to different levels of u you can change by changing the gradient. Similar things you can do for v, right, or for what you do is you for different values of the gradient and the same time you will get a different v, right, and then you keep v u constant and you can sample that way also, right. So, that is typically how it is shown in all these images and all these pulse sequence pictures, which is I have not shown them here, but maybe at a later time I can actually show you how it is done, okay. Because typically the range of these gradients are shown, because the gradient can go from some minus max to plus max, right, and that is I have not shown here in any of these diagrams, but that is how we typically have to interpret it. We will look at some more some of these more practical image acquisition pulse sequences, right, but this is just to understand the model for your acquisition, right. This is the model of the signal and how you can encode your position, right, using these gradients. That is a fundamental concept that we would like for you to understand. So, that is how it works, and that f of x y, that function that you are measuring, as a function of position is basically that has both the terms, that has all the relaxation time terms as well as the magnetization density in it, and that is it is just a complicated function that you measure. And so, your images that you measure in MR are both functions of so called spin density, which is basically the magnetization, as well as the T1 and T2 relaxation times. These are basically the physical quantities that you are actually trying to measure by using MR images, right. So, this is in contrast to CT image, where the quantity you measure is actually a function of electron density, right. It is mu you are measuring. For example, in CT images we saw you are measuring mu, where mu is the attenuation coefficient, which itself is a function of energy and atomic number, right, but it is actually more a function of density, right. So, what you are measuring is basically the density, the actual physical density of the object that you are measuring. In this case, you are looking at magnetization density as well as some relaxation time properties. So, this is more of a nuclear property that you are measuring, right. This is the property of the nucleus you are measuring, the specifically water. So, in CT you are actually measuring electronic properties. So, it is kind of similar, but kind of different that way. The sensing mechanisms of course are also different. Okay. Okay, so one of the commonly used, or say the practical, should I say, I would not say commonly used. So, the way the FID decays rapidly due to different effects, right. One is the magnetic field inhomogeneities. Okay. So, the spin echoes are basically this you can generate these spin echoes till your signal is completely lost due to T2 effects. Okay. How do you generate this spin echo, right? So, that's what we want to get at. Before we go there, we just have to understand that the echo, that is FID, that is generated, right, it decays due to the T2 effects as well as the T2 star effects, right, and this is very rapid decay. So, measuring that is slightly difficult, but if you get a spin echo, then you can measure that much easier, because this FID is generated instantaneously as soon as you flip the spins into the plane. FID starts generated and it starts to die away, right, because the dephasing effects or the defocusing effects of magnetic field inhomogeneities and the spin interaction is very fast, right. These are milliseconds or less. So, in order to get some more time for measurement, so instantaneous measurements are not possible. So, you get better, and also to get a better amplified signal you measure spin echoes. The spin echo is basically generated by applying a 180 degree RF pulse after the initial tipping pulse. So, you tip the spins into the plane or at some angle alpha using the RF pulse, and then you apply one more pulse which will flip it another 180 degrees, right. So, it basically reversing it, or if you think of it as a 90 degree flip, it flips into the plane, and then if you do the 180 degree, it will just flip out the opposite direction. So, what does the 180 degree pulse do? The 180 degree pulse reverses the phase relationships. So, if there is rapidly dephasing, so as soon as the spins are flipped into the plane, it starts to dephase. So, once you flip one more 180 degrees, the direction of dephasing is the same. So, they will actually come together again to give you another echo, so another signal. Okay. So, how do you interpret this 180 degree plus? We can interpret it as sudden change in the sign of the frequencies both along the x and y axis. Okay. So, if the prior to applying the pulse the k position was uv, then post application this can be interpreted as minus u minus v. Okay. So, this enables a lot of what you call image acquisition tricks. We will not go into details, but the 180 degree pulse, the spin echo pulse is what is typically measured. Okay. Let us look at the sequence. Okay. So, slice selection 1 on top, you see that numbers have written. 2 is the phase encoding step, I think yeah, that is the GY gradient being applied. Following that you have the 180 degree RF pulse along with the slice selection. Okay. So, you got one more slice selection gradient, and then you wait for a particular period of time, this time to echo, and along with that you apply the readout direction, right. So, if you are not sure, right here is the phase encoding, This is the 180 degree pulse with the you have to do the 180 degree pulse with the gradient slice selection, because you want to do the flip in that particular section, right. Once that is done, after waiting period, you apply the readout direction pulse and you get an echo. Okay. I have not drawn the echo here, but this is the general spin echo sequence, which is kind of a more practical sequence. Okay. The pulse repetition interval, this I spoke briefly earlier. So, in order to acquire all of 2D space, right. So, we are looking at now, if you look, we just looked at one value of gx and gy. So, in order to acquire all of 2D Fourier space, the basic pulse sequence must be applied with different scan parameters. Okay. So, for what I mean by scan parameters, right. So, for polar scan, it has to be done at different orientations theta. Okay. And then all techniques must be repeated using different phase encoding gradient values, right. You change the gy, then you get a different v, right. So, this gives you different v's, right. And so, every time, so you have you apply one gx, one gy, sample the signal, you wait, and that waiting period is the pulse repetition. You wait a little bit because you want everything to get back to its stationary state, and then you repeat the experiment. Okay. So, in this fast and slow are possible. Slow meaning you have to wait a considerable amount of time before you do the next repetition. Okay. And fast is you do not really wait, but you continuously acquire. So, there are, and then each of them has its advantages and disadvantages. Okay. There are some other things also that I have not shown. So, in all the figures, right, I have shown the gradients to be turned on instantaneously. That never happened, there is a slope to it. So, it is not instantaneous. Okay. And multiple phase encoding gradients, I have not shown that at all, but it is typically that is required to transverse K space. FID is not acquired, right, only the echo signal is acquired, that is the only possible thing to acquire, at least that is the understanding. So, the echo signal is a better signal to acquire, not the FID, all right. Okay. So, what do you do with the images, right. So, data acquired from 2D MR imaging, what we have seen are called 2D MR imaging pulses. And we saw that when you write down the signal model, it can be interpreted as scan of Fourier space. Okay. So, taking the inverse Fourier transform will yield the image, but then it is not a simple inverse Fourier transform, you have to do a discrete inverse Fourier transform, right. So, then the third problem that other problem that we also talked about is that the interpretation is not very straightforward, okay, because the meaning of what you are reconstructing cannot be explained very simply, like CT I said, right. It is a attenuation coefficient, it is a function of density, electron density or physical density of the object, or radionuclide imaging wherein what you reconstruct is basically the radio tracer concentration. And so, but then the problem is here, it is not so straightforward, but we do know that f of xy we saw has multiple quantities in it, depending on how you choose the time to image, right. For instance, imaging parameters like time to echo and pulse repetition time, they can encapsulate multiple properties. So, for instance, one property is the spin density, which is proportional to the magnetization. The other property is the T2 relaxation time, one more property is the T1 relaxation time. These are the three important properties that are captured by an MR image. Okay. And that is also the quantities that give rise to contrast in these images, like for instance, some tissue appear bright, some tissue appear not so bright or darker, and those depend on how you tweak these time to echo and pulse repetition times.